All right, so here we are in Chapter 2. Let's start with 2.1. And in Chapter 2, what we're going to be doing is talking about how we see these microorganisms. So basically, we're going to be talking about different types of microscopes, the use of different types of microscopes, meaning why we would use different microscopes for different things, and then how it is that we're going to be making things visible with those various types of microscopes. But first, before we get into the microscopes and into the different types of contrast, meaning the different dyes and things like that that we would be doing, the stains, we need to talk about the properties of light. So in chapter 2.1, we have the properties of light. So we're going to be talking about kind of the specifics of light so that when we get to the microscopes, we can understand them better and what it is that we're talking about and what it is that we're working with and why we see what we see. So first of all, just kind of part of the basics, if we recall from previous courses, that light is a wave. And so we're going to take a look at those different properties. So if light is a wave, so we have light coming in, and we have it as a wave, then we have different parts of that we can identify. So one of the first parts that we can mention is the wavelength. So wavelength. And when we talk about wavelength, that's the distance between one peak and the next. So if we say down here, which would be a trough, the distance between these two troughs would be the wavelength. The distance between these two peaks here would be the same distance, would be the wavelength. So between two peaks or two troughs. So wavelength is the distance between one peak and the next peak. So that's going to be our wavelength. And we can see, and we'll take a look at different waves and therefore different wavelengths. You can see that the distance between the peak here and the peak here is going to be smaller, a smaller wavelength than the distance between the peak up here and peak up here, or likewise the trough here and the trough here. So we have different waves that have different wavelengths. Another definition that you need to be aware of is amplitude. And amplitude is the height of the wave. So rather than the distance between the two peaks or the distance between the two troughs, what then we're talking about is if we took an imaginary line and put it right down the middle of our wavelength, what we're talking about is that height of the wave, is our amplitude. So from that imaginary line in the middle there to the top, to the peak, this area here, this space, is the amplitude. And similarly, if we take our imaginary line that's in the middle and we go to one of our troughs, this same space here is the amplitude. So the height or the depth of the wave is our amplitude. And so we're going to talk about the importance of each of these. Before we do, though, then let's talk about the third one that you should be familiar with, which is frequency. So the frequency then is the speed of the wave. So the speed of the wave. And what that means then is that we're talking about the number of wavelengths per unit of time. So the number of wavelengths in a certain amount of time. So if we were to take, whatever this is from here to here, let's say 1 second, and we count the number of waves that happened between those two periods of time, then that's going to be our frequency. If we then say that from here to here is the same amount of time, let's say it's 1 second, then we can say that that has a particular frequency. So we could count the number of wavelengths in a given amount of time, and the number of wavelengths in one wave compared to another wave is going to give us different frequencies. So different speeds, essentially. And so then we have higher frequency waves and we have lower frequency waves. And we're going to talk about why that is important when we get to our visible light spectrum, where when we talk about our visible light, those are all the things that we can see. And we can think of that in terms of a rainbow, for example, from our red light all the way to our violet light and everything in between. And each one of those colors and everything in between has different wavelengths. And those different wavelengths are then going to allow us to see those different colors. And we'll talk about that. And we see that when we put that white light, for example, coming from the sun through a prism, through a lens, and then that can spread out. It refracts those different wavelengths and we can see the different colors. So we'll get into that in more detail. But starting out here, we have our wavelength, which is the distance between one peak and the next, our amplitude, which is the height of the wave, and then our frequency, which is essentially the speed of the wave, which is our number of wavelengths per some unit of time. So then when we are talking about the way that light behaves, so if we can take those things into consideration, we have our high frequency and our low frequency, and those are all going to behave differently based on those three terms that we just spoke about. Now what we want to talk about are the interactions of light, because we're going to be utilizing this information when we talk about microscopes and how they interact with each other and why it is that we see things with different microscopes. So the first term that you should be familiar with is reflection. And reflection is when light bounces off a material. And you can kind of keep this term in mind or understand this term because we see our reflection in a mirror, for example. So it's the light from us, that's bouncing back at us. So light bounces off a material. And so that is reflection. So when we have wavelengths of light and then it bounces off a material, then we can see that. So for example, the text talks about a red piece of cloth. It reflects that red light to our eyes, but that particular cloth is going to be absorbing all of the other colors. So it has white light from the sun or from a light bulb coming in, and then what's happening is that cloth is going to absorb some colors, and it's going to allow the bouncing off of or the reflection of another color. And so if it is red to our eyeballs, what that means is that it's reflecting that red wavelength back at our eyes. And what it's doing is it is absorbing all of the other wavelengths. And that's why it looks red to us versus something else that may look blue. If something looks blue, then that means it's absorbing the other wavelengths and it is bouncing back the blue wavelength to us. So that's reflection, where it's bouncing off of a material. The next term you should be familiar with is absorbance. So absorbance is when the material captures the energy of that light. Or of the light. So I did just use that in terms of the cloth example where it absorbs things. So we can think of something absorbing heat, for example. In that same way that something can absorb heat, we can think of it as absorbing energy of light. So some things absorb certain wavelengths or energy of light, and other things absorb other things, just like I just mentioned with the red cloth versus the blue, for example. So the blue cloth is going to absorb everything but blue energies of light, and then the red cloth would be absorbing everything but the red energies of light. And then some things they can absorb, like the glow in the dark stuff, the glow in the dark stars or putty or things like that. They can absorb this energy of the light, and then it is emitted later. And so there's this absorbance. All of these materials that are around us absorb a certain amount of wavelength or a certain energy, and then some of it reflects back. But then also the next term that you should be familiar with is some is transmitted. So the next term is transmittance. And transmittance is the light that travels through a material. So you can think of absorbance and transmittance as sort of opposite terms. So as light is going toward an object, so if we're thinking in terms of microscopes and we think that we have something on a slide and we shoot light through it, some of that light is going to be absorbed by the thing that's on the slide, and some of that is going to be transmitted through. So we transmit it through, meaning the light travels through that material. So when we are looking at different objects, we adjust the amount of light that we are allowing to go through an object based on how much it absorbs and how much it transmits. And we can adjust that light using various parts of the microscope. This is also important when we do certain types of reactions in order to quantify something in a test tube or a cuvette. So there are certain machines that can test the absorbance of something or the transmittance. So for example, we have a cuvette is kind of a square test tube that typically has lines on one side, and then you place in your substance. So if we're talking microbiology here, sometimes there would be the need for quantifying the amount of a particular bacteria, let's say. So if we have some sort of bacteria solution and we have that in there and we want to quantify it, we want to know how much bacteria is in there. One of the ways that we can do that is we can put a certain amount of the solution inside of this cuvette. And then what we can do is we can add another chemical to it that will cause a reaction. And so the amount of reaction that happens then is going to tell us how much bacteria is in that cuvette. And so a lot of these things will be very small distances or very small differences between the quantity of bacteria, and therefore very small differences between the changes in that reaction. However, a lot of these reactions or ways to determine this are going to make it so that a certain amount of light is moved through the material and a certain amount of light is absorbed. So you can actually take this cuvette then and you can put it into a machine. And when you put it into the machine, we have our solution in here, and it has already undergone a reaction. We add whatever chemical that we decide we want to put in there, and then when we put that chemical in there, we have that reaction. And then we can use this machine called the spectrophotometer. The spectrophotometer is going to shoot wavelengths of light, different wavelengths of light, through the solution. And then what comes out the other side is going to be our transmittance. And so then we can have a number for transmittance, how much comes through. And then we can measure another cuvette, for example, with another amount of solution, and then we'll shoot the same wavelength of light through it, and whatever gets through it is the number of transmittance there. And we can see if there is a higher or lower transmittance number that will indicate to us if there's more or less of a reaction. And if there's more or less of a reaction, then that can tell us how much of a bacteria we have in there, for example. Or conversely, it can measure absorbance. So we can see how much is actually absorbed by the material, by the solution. So it would be the light staying in there, right, being absorbed by the solution. And then again, whether that's high or that's low, will tell us how much of something we have in there. So how much of a reaction has occurred, and therefore how much or how many bacteria are in there. We can do some calculations. So not only is it important for different microbiological processes down the road for quantifying bacteria, but it's also helpful when we're talking here about the microscope and adjusting our light, how much light we're letting in, adjusting the diaphragm to open up or make smaller the space that light is coming through, so that we have differences in absorbance and transmittance. And we can adjust our focus and we can adjust what we're seeing based on these properties. The next term that you should be familiar with is then transparency. So transparency is allowing the light or some light to pass through. So allowing light to pass through. So you can kind of think of this. We know that glass, typical clear glass is very transparent versus a wall is not very transparent, for example. And, if you remember old school transparencies, which are, kind of plastic pieces of paper that people printed on and put up on an overhead projector. So they're transparent. It allows light to move through them or pass through them. And then opposite to that is opacity. So these are kind of opposite terms here. Transparency is allowing the light to go through. So we would say in this case, when we're talking about the difference, for example, between transmittance and transparency, we would say that the object is transparent or has transparency. And then what that means is it allows light to be transmitted through the material. So that's the difference in these terms here. And likewise, the difference between absorbance and opacity or opacity. So opacity is restricting the passage of light. So passage of light through a material. So again, we would say that something is opaque, like a wall, for example, or a textbook is opaque. But then what we would say was the amount of light that is absorbed by that book or that wall is some number. So the material itself or the object itself is described as in terms of opacity or opacity and transparency, and then the light, how much light gets through, is quantified in terms of or is described in terms of absorbance and transmittance. All right. So the next term then, when we are moving into how light works, so we have some of these definitions now, and what we can talk about next is the interactions of these lights, of these light waves. So the first one is interference. And interference, as you can imagine, is the interaction of light with itself. So the interaction of light with itself. And then this changes the pattern of the motion. So we'll add that in there too. So changes the pattern of the motion. So when I think of interference, what I often think of is if we had a pond and if we drop a stone in the pond, we know that that's going to have waves that come off of that stone when we drop it in the pond. And then we can drop a stone over here as well, and then we have the waves that come off of that one. And then we know that right here we're going to have interference. So that is the interaction of light with itself. In this example, we're talking about waves because light is waves. So the example of the pond would then be waves that are interacting with themselves. So we have waves in the pond, and we can even say, if we're talking about with itself, these waves of our first stone here are going to go out until they, let's say, reach the edge of the pond, and then they're going to start moving backwards, interfering with themselves. So that's interference, is when we have these light waves that are going to be changing the pattern. So our initial stone being dropped is going to make this nice wave pattern moving out, but then once it bounces into something else, like say the edge of the pond here, and starts to go back, then we're not going to have these perfect circles of waves. Then we're going to have interference, and it's going to change the pattern of the motion. So that's interference, and we see that also when we're talking about microscopes, because we have these objects that we're putting on the slide in the path of light, and so then in that path of light we have light interacting with what we could call these stones, which is what is on the slide itself. And so then light is going to be hitting these stones, quote, stones, or objects that we have on the slide, and then there's going to be some differences. There's going to be changes in the pattern. So the light is going to interact with itself as those light waves are going through whatever it is that we have on the slide. And then the next term is diffraction. And diffraction is the bending or the scattering of light when it interacts with small objects or openings. So the bending or scattering of light when it interacts with small objects or openings. So if we think about this example that I just gave with the pond in the water, if, for example, we had, say, a weed here or something, a plant, when we drop this stone in and we have those waves that are going, then those waves are going to interact with this plant. This is, kind of we're looking down at it, so the plant would be coming up toward us. So the waves then are going to bend and move around this object here, so this small object. You can also think of it if we were to take a look at the other side here. Let's say that we can, we have an opening. Let's say that there's kind of a stream or something here, or there's some rocks over here, and then the pond keeps going to the other side. So if we have waves from our stones here, that once they reach this area, they're going to be bending and they're going to be reacting differently once they go through that small space or that small opening. So you can perhaps imagine this as you think about stones and as they interact with spaces, then they're going to change as they move through that small space. And so that's diffraction. We can see that the diffraction gets greater as the objects get smaller than the wavelength. So if, for example, this space between the two stones here is quite small, and it's close to the wavelength distance, the distance of the wavelength, or smaller than that, then we have a greater diffraction. So we have increased diffraction as object or opening gets smaller than or equal to the wavelength. And I think that you can imagine this too, like if we took these two stones and if we put them, one was over here, one was over here, and these two here didn't exist, and really the opening was between this rock and this rock, we can see that this wave isn't going to have much difference, much change. There isn't going to be much bending. So that's because that the diffraction is less than, so the opposite of this here is that the diffraction is less when the opening is larger, and further, much larger than the wavelength, for example. So then what we see is that diffraction usually causes interference. So we usually see that when we have this diffraction, this bending of light around an object or around an opening, that as we're moving between this, then we have some sort of wave moving here, and we have some sort of wave that ends up moving here. The wave tends to kind of split in certain ways, and then we have an interference effect happening here where the waves are kind of interacting with each other. And when we talk about interference, then we can talk about the ways that they interfere. And so we can change the patterns there based on how those different things interfere with each other. And so we see that interference happen oftentimes when there is diffraction. When we have something in the way, something small or an opening or something like that is going to cause that interference. So the next term that we want to talk about that we're going to spend some time with is refraction and refractive index. So refraction is when a light changes direction when entering a new medium. So when light changes direction when entering a new medium. So the reason that we have refraction, so if we are sending a beam of light and say we're sending it through one medium, and then that beam of light is going to start to go through another medium. It runs into and starts to go through another medium. We have this change that happens. This is refraction. It changes the direction of the light. And so refraction is caused by a change in the speed of light when it enters that new medium. So we can say that it's caused by a change in speed of the light when it enters the new medium. And furthermore, that the amount of refraction, so the larger the difference in that direction change, is dependent upon or partially dependent on the angle of the incidence. So the angle that it's coming in, we're going to see different amounts of refraction. So the amount of refraction, or the change in direction, is partially dependent upon the angle of incidence. It's also partially due to our refractive index differences. So we're going to talk about that in a moment. So our refraction. We can think of refraction in terms of if you have ever had a glass of water sitting on a table and you put a straw in it. If you look at the straw, if you just take a look at you're looking at the cup or the glass, you can lift it up and take a look at it from the side. You can see that the straw, so if we have our glass and then it has some water in it, and then we put our straw, it's just a regular straight straw, that when we put the straw in and we look at it, it looks like it moves over and it changes where it's at in the water. And that's because when we're here, we're looking at that. So the light that we are picking up with our eyeballs is going through air here. And so we see the straw in a particular location. And then when we are looking at it here, our eyeballs see it here, it's going through water. And so we have a change in the light, which is the refraction. So you can see that the straw looks like it's at a different location when it's in the water portion. And that's because of the refractive index of air versus the refractive index of water. And so we have a change of speed in the light that our eyeballs are seeing when it sees this in air versus when it sees it in water. So let me write down refractive index. So our refractive index, or the RI, is the extent to which a material slows transmission speed relative to a vacuum. So basically just what that means is that if we take a vacuum, light, if we shoot light waves through it, it goes a certain speed. Those light waves go a certain speed in a vacuum. Now, if we shoot those same light waves, the same wavelength, in air, it's going to go a different speed. If we shoot it through water, it's going to go a different speed. If we shoot it through oil, it's going to go a different speed. If we shoot it through glass, it goes a different speed. So when we are putting light, or we're seeing light, because that's light going to our eyeballs, when we see it through different medium, or media, then we are going to see things differently because of the refractive index, because of the differences between in this example, let's say air and water. The speed with which the light from this straw is reaching our eyeballs is different in air as in water. And of course we have the glass in there, but that's a control because we have the glass in the air portion and the glass in the water portion. But perhaps up here it would look a little bit different because there's no glass in this area. However, the difference between the glass and the air in this case is so minimal, we don't really see a difference there. So our refraction is when the light changes direction, when it enters a new medium. And that's because we see a difference in the speed of light when it goes through the medium. That difference in the speed of light, or the different speeds of light that go through the different medium, is called the refractive index. So each medium, so air, water, oil, etc., has a different refractive index. And the reason that that's important is because then we can say that the larger the differences in the refractive indices, the larger the amount of refraction. So when we see the difference, as I was mentioning here, between the air of the straw that we're looking at here with no glass, or down here, the air with glass, the difference between the refractive index of glass and the refractive index of air is not very great. So we're not really seeing that kind of the straw jumping to a different location between the air with no glass and the air with the glass. However, the refractive indices are very different between the air here with the glass and the water down here with the glass. And since those refractive indices are very different, the air versus the water, then we see a larger amount of refraction than we do between up here, the air with no glass, and the air with the glass. Now this is important when we talk about microscopes. So in the text, the image shows the glass, and it shows that we are shooting the white light, or the light is going through the glass, and then they have it fancier here, but then we have the glass slide, for example, and then we can see that the light changes and then it moves back out. So in this case, this is our refracted light. And that's because we have that difference in the refractive indice over here and the refractive indice over here, or index here and index there. And then the difference there is causing that refraction to occur. So then when we are talking about microscopes, that is important because if we're thinking about a microscope, let's just say kind of in general. In general, we have a lens here, let's say, in the part where we're looking. This is our eyeball here. We're looking down here, and then here we have our slide, which is made of glass. And we have our lens here, also made of glass. In between here we have air. So then we have our stage, and then we have light coming up from our light source. And it's going to go through the slide here, which is made of glass. Then that light is going to go through the air here, the space between the two. Then it's going to go through this additional lens here. So each time it moves through these different media, then it's going to be refracted slightly. So what we're doing is we are, in general, depending on the type of microscope, we want to decrease the amount of times we have refraction. Because when we have refraction, then what happens is we are shifting that light, we're bending that light, and then it's going to not give us as accurate of an image as we want to have. So when light is moving from a low refractive index material to a material with a higher refractive index, then it's going to also refract away from its previous path and into a direction that's more perpendicular. So if we're going from a low refractive index, let's say this is our lower refractive index with the air here, and then it's going to go to, let's say, this lens here, or even let's say down here. So we have our light here, we also have air coming down here. So this is our low refractive index down here. Light's going through it, it gets to the slide, the glass slide, and then it's going to bend slightly. It's going to bend to be more perpendicular rather than lining up to be more parallel. And so we're going to be losing some of that image. It's going to be shifting or adjusting that image slightly, and then we reach air again, and then it's going to go even more. Let's say it goes this way, then we reach this lens up here again, and it's going to go, say, more this way. And so it's bending the light each way. And so we want to kind of minimize that. One of the ways that we minimize that is by, on our high-powered lens, our 100x objective lens, which we'll talk about more in detail coming up. What we do is, instead of having air here, we add immersion oil. And what that does is we put kind of this glob of immersion oil here, and our immersion oil has a refractive index that's closer to the slide, the glass slide, than air does. And so what we see is we have less of a refracted light going between the slide, the glass slide here, and then the oil here, and then the glass here. So what we're doing is we're losing less of that light, losing less of that image, because we're adding that oil there that's going to decrease the differences in those refractive indices. Okay, so I have mentioned here now, we've talked about some lenses. So let's talk about what a lens is. So a lens is an object that has a curved boundary or a collection of prisms, and then it's going to collect all of the light that strikes it, and then it's going to refract it. So we just talked about refraction. So let's say an object with a curved boundary. So basically meaning, typically it's glass, right? So we have glass or plastic where it has a curved edge. Or a collection of prisms that collects all the light that strikes it and refracts it so it all meets at a single point. So when we think of a lens, if we think of a microscope lens, or even glasses, like if somebody has a difficult time seeing clearly and you have to go in to the doctor, to the optometrist, I apologize, the optometrist, then you may be prescribed glasses, and then those glasses would have lenses. So when we think about lenses, we can think of a lens that looks like this, which is a convex lens, or we may be prescribed or have lenses that look something like this, which is a concave lens. So our convex lens and our concave lens. And what we're saying about a lens is that it collects all the light that strikes it. So we have our light coming in here, right, into our lens, or the light coming in here to our lens, and then it's going to refract that light because we have this curved boundary here. Since we have a curved boundary, the light's going to hit the lens, and then because of the curve, we're going to see that light bend. So we're going to see that refract. It's going to refract in such a way to where it meets at one point. This point is called the focal point. We see the same thing with the concave lens. The difference with the concave lens, however, is that the concave lens is going to focus the light back in this direction because of the way that it's curved. Since it's curved in a concave way, the light actually is bent back and refracted this direction, and we still have our focal point here. So what we're doing then is we are, in my example of the microscope up here, we have all this light coming in, but we want to make sure that we can get the best image possible of whatever it is that we're looking at. And so then we have lenses that are going to be bending that, refracting that light to a focal point that is on our eyeball. So it's going to be refracting it to our eyeball. And this is where we're talking about focusing something. So when we try to focus something, what we're doing is we're moving various parts of this equation in the microscope here to make it so that this focal point lines up with our eyeball. And that is, again, why we have different people. When you look at different microscopes, you might need to adjust things a little bit, adjust the spaces, because different people are going to have different focal points. Their eyes will be at different locations. Perhaps one person has a little bit of myopia. Their eyes are myopic, meaning that they're not seeing clearly, so they need to focus things differently. So we have this focal point or this image point, and that's where all of the light is bent and refracts toward. So let me just write that down. So focus or focal point is a point at which light is bent or refracted, to use our correct terms here, refracted towards, and it's usually by a lens, because that's the point there. Good. So our focus, and then let me say further that our focal point is specifically the point. So let's just say this is focus, is a point at which light is bent or refracted toward, is getting something into focus. And then we'll say the focal point is the point at which a beam of light converges or appears to emanate from. The reason that it says converges, if we say converges, what we're talking about is our convex lens, because it converges at this point here. And then our emanate, so it seems like it emanates from, in this case, we're talking about our concave lens. Oops. What we're going to focus on in this class, because it's what is most useful in microscopes, are our convex lenses. So we can really just kind of familiarize yourself, make sure that you understand the convex lens and how it comes to that focal point because of that curved border. All right, so then when we do talk about convex lens, let me put that here. So if we talk about our convex lens, then what we're saying is that this is a lens that has a focal point that is past the lens, that causes the light to bend inward. So that's what we're seeing here with the drawing or with the image. And this causes magnification of the image. So lens with a focal point past the lens, causing the light to bend inward. And then this is causing magnification of the image. And of course, this is why we're talking more about convex lenses, is because we're trying to magnify the image. We want to make sure that we can increase it so that we can see it, because oftentimes we're looking at very small things. Good. And so then conversely, we have our concave lens. And so our concave lens is a lens with a focal point before the lens, causing the light to spread out. And then this makes images appear smaller, which is not typically what we're doing in microbiology, because we want to make things bigger. Sometimes, however, this is used in microscopes to redirect the light path. And we'll see that later when we talk about the different microscopes. One last thing that we want to mention with regards to our focus or our focal point is focal length. And so focal length is the distance from the focus or the focal point to the lens. So if we look at our image up here, we have This is where our lens is located. This is our focal point, so then just the distance between the lens and the focal point is our focal length. So distance from the focal point to the lens. And this is important because as we're talking about microscopes, what we're going to be adjusting or shifting is the focal length. We're going to be moving the lens or moving the stage so that we're shifting or changing the distance between our image and our eyeball essentially. So, and we have some lenses between those two. So we're going to change the distance from the focal point, which is our eyeball, to the lens. We'll be moving the lenses so that we can get things into focus. Great. So that kind of summarizes a lot of the background in light and waves, so the different properties of light. We're not done with this section yet. The rest is kind of a small piece. So I just want to make sure that you're clear about the different terms that you need to be familiar with. So you should be familiar with wavelength and amplitude and frequency. You should know the terms, the way that light interacts, and how we can quantify these different things like reflection, absorbance, transmittance, transparency, opacity, interference of light waves, the diffraction, and then of course refraction. And that is a really big one. The refraction is important because we're talking about our refractive indices, and when we are talking about how things interact when they are going through, or the speed, that's important when we talk about microscopes and we're talking about magnification. All right, so the next section is talking about the electromagnetic spectrum. So when we talk about the electromagnetic spectrum, what we're talking about is electromagnetic radiation. And that's the radiation that's composed of different types of electro, and magnetic waves. So this is our light waves, our radio waves, our microwaves, our X-ray waves, all of these different waves that are around us. What we are going to focus on in this class is our visible spectrum. So our visible spectrum are between the wavelengths of about 350 to about 800 nanometers. And this is where we see, this is what we see when we think of our rainbow, for example. When we think of the rainbow going from our red to our blue or our violet, this is our visible spectrum. All of the wavelengths that we can see, because this is what our lenses and our eyeballs are going to be able to separate and allow us to see. We can't see the other things like the ultraviolet light and the X-rays and the infrared and the radars and all of these other types of waves that are moving around us. What we see is the visible spectrum, which is why it's called that. So in general, when we have a high frequency wave, we have a low wavelength, and that means that it is high energy. So this is important because when we think of light, it can be seen as light as in waves, but then light as a particle. These are these photons that are moving in waves. So when we have higher frequency, then we have higher energy. So we have more and higher energy photons versus the opposite then. So when we have lower frequency, then we have lower energy. White light contains all wavelengths of visible light. Wavelengths of. So the light coming from the sun, it looks white. It's our white light. It contains all the wavelengths, and it's not until it interacts with something that's going to provide those different colors. As we mentioned, if we have the red cloth, our white light comes from the light or comes from the sun. It's going to hit that red cloth. It's going to absorb some of these wavelengths of the visible spectrum, and it will reflect other wavelengths. In this case, if it's a red cloth, it's reflecting back those red wavelengths, and it's absorbing all of the other wavelengths. So our white light, and that's where you can also see, you've probably seen the prism, and then you have the white light coming in, and then what's coming out of it is the rainbow on the other side. And that's because that's a lens, and what it's doing is it's separating out all of the wavelengths. And so then we see the rainbow on the other side because we have that separation of our visible light spectrum. So also going along with these different wavelengths, we have our red color. This is our long wavelength. So red is a long wavelength, and it has a low frequency. And conversely, our violet, the other end of the spectrum, the visible spectrum, has short wavelength and high frequency. And then, of course, we have everything in between. So we have the red, the orange, the yellow, the green, the blue, the indigo, the violet. Things are between there. Also, what's different between them is that when we have our different frequencies of light, we have different refractive indices. So our refractive index differs for different frequencies of light. So again, we have our refractive index, our difference in the speed of light is different for our different frequencies of light. So the red is going to be moving in a different at a different speed than our violet, for example. And this that we talked about, or that I mentioned up here, this is called dispersion. So you should be familiar with dispersion also. So dispersion is, I'm going to put it down here also. Dispersion is the refraction of light into different frequencies. So what we're talking about then is we have light that's moving into our prism here, into our lens, and then it's going to refract those into their different frequencies. So we have the different frequencies here depending on the different colors, and they're different colors because they're different wavelengths or different frequencies, and that's how our eyes see them, is those different colors. So what else is mentioned in this section of the electromagnetic spectrum is fluorescence versus phosphorescence. So fluorescence is absorption of a light energy that is then emitted upon relaxation of electrons as light energy, and that's usually a lower energy. So if we think of fluorescence, something fluoresces, oftentimes what we can think of is some of that fluorescent putty, the glow-in-the-dark stuff, or the stars, or something like that, where we can see that it is going to absorb, or it has absorption of light energy. So you have to put on the lights, turn on the lights so that it's absorbed, light energy that is then emitted upon relaxation of electrons as light energy. And then this is usually of a lower energy. So some of this energy is absorbed, it goes into the energy and vibration or motion of the molecules or atoms, but then it can be released, and then it relaxes and those electrons are released, and we see that as a fluorescence. This is important because we have certain dyes. So the FITC dye is what the text mentions. So it absorbs the UV light, and then it emits green. So absorbs the UV light, and then it emits green, so it can be used as a dye. We can expose something to the FITC dye, and then when we expose it to the UV light, then it can emit green, and we can see that in a microscope. There's also the Texas red dye. It absorbs the blue light, and then it emits the red light. So then we can see that. And then the text also mentions phosphorescence. And so this is very similar to fluorescence, where it absorbs the light, and then it's followed by the emission upon the relaxation of electrons. But they have remained in an excited state for a longer period of time. So the electrons have remained excited for a longer period of time. And then what this means is that phosphorescence can last longer and be seen longer. So these are two things, and we're going to talk more about dyes in a future section here in Chapter 2. But when we're talking about light, we can see that things can absorb that light and then they can emit it later. And that's important when we're talking about different dyes, like the fluorescence dyes and the phosphorescence dyes. So then in the last portion of this, we talk about magnification, and then we talk a little bit more about resolution. So magnification is important when we're talking about our microscopes because we want to be able to indicate what magnification we're using. And we can go up in magnification so that we can see an image better, so that we can see something better. So magnification is the ability of a lens to enlarge the image. Enlarge the image of an object relative to the real object. So magnification, I think that most people are typically familiar with magnification. We're magnifying something. You think of a magnifying glass at the least as a lens that is going to make something that's smaller look larger to your eye. And we use these lenses for magnification in our microscopes so that we can take something that's very, very small and we can magnify it to make it look larger than the real object actually is. So for example, we have different magnifications. If it's a 10x magnification, then that means it's 10 times larger than when seen with the eye. So then it normally is when we're just looking at something. We're going to talk more about microscopes and microscope parts specifically, but when we have microscopes, we have our objective lenses. Our objective lenses typically come in 4x, 10x, 40x, and 100x. So then that would mean 4 times larger, 10 times larger, 40 times larger, and 100 times larger are those objective lenses in our bright field microscopes that we would typically find in a laboratory. Then we also have our ocular lenses. And ocular lenses are typically 10x, so that makes the image 10 times larger than even that. And we're going to talk about how we can calculate our magnification in the future here. So just note that if it's 10x, for example, that means it's 10 times larger than if we were just looking at it with our regular eyeball. So the last portion that we want to talk about is our resolution, and this is really important to magnification and to utilizing microscopes to see these small things like these microorganisms that we'll be talking about throughout the semester. So our resolution is the ability to tell two things apart, basically, through a microscope. So the ability to tell that two separate points or objects are separate. So the ability to tell that two separate points or objects are separate. So resolution, as it says here, is if we are looking at something through a microscope, how well we can tell the difference between two things is how the higher the resolution. So the higher the resolution, the easier we have, the easier the ability to tell the difference between two different points, between two different objects or two different points on the thing that we're looking at. If things are very, very blurry, very, very fuzzy, and it's hard to make out the difference between those 2 points, we would then say that's a low resolution image. There are 2 factors that affect resolution. So one factor is the wavelength. So if we have a shorter wavelength, it can resolve smaller images. Or smaller objects, I guess. Objects, not images. So for example, if we have an electron microscope, we'll talk about in more detail, but an electron microscope utilizes electron beams. So it's shooting beams of electrons at the object that you're trying to look at. And our electrons have a very short wavelength. And since they have a short wavelength, we get very, very good resolution with our electron beams in our electron microscope. Compared to our bright field microscopes, which are our typical laboratory light microscopes, where the wavelength is much longer than the electron wavelength, and so we don't get as great of a resolution from our bright field microscopes as we would with an electron microscope. The second factor that is important or affects resolution is the numerical aperture. So the numerical aperture is a measure of the lens's ability to gather the light. So a measure ability to gather light. So the higher the numerical aperture, the better the resolution. So the higher the numerical aperture, the better the resolution. So if it can collect more light from that object, the more stuff it can collect, the better the resolution that we're going to have. So if we have a lens that doesn't collect very much light, or it's very, very small, we're not going to see as much resolution. So another factor here that we need to take into consideration when we're looking at things in a microscope is contrast. So contrast is the difference between the brightness of various details in an object. So the difference between, I'm running out of space here, between the brightness of various details in an object. And we'll talk more about contrast and why that's important, but this is why we use dyes. We use dyes on our specimens so that when we dye them, we can create contrast. Typically, if we put a single cell on a slide, so a cheek cell, for example, if we scrape the inside of our cheek and we put that on a slide, there's not going to be much contrast. They're kind of see-through, kind of clear, and so it's difficult to see them. However, if we do apply a dye to it, then we're going to increase the contrast. If we increase the contrast, then we're going to make things visible, more visible. So we're adjusting the brightness of various details in an object so that we can see it more clearly. So the last thing that I want to say about this is that the resolution is something that's very, very important to a microscope. And so the resolution, again, is the ability to discern two objects as being separate. So if we can see the two objects as being separate, so we have our magnification, which is making things larger, and then we have resolution, the ability to determine two things as separate. So the things that are going to affect that resolution again are the wavelength, so the energy of light that's coming in, and then our numerical aperture, so the amount of light that's coming in. And then what we also need to take into consideration, all of the other things that we talked about, like when we were talking about our refractive index, our refractive index or refraction is something that is also going to affect our microscopes. So our refraction, we already talked a whole lot about refraction, and remember that we talked about it with the lens, for example, and then we put oil on that lens, and then we have our ocular lens that goes up to our eyeball. And that's because we don't want to lose this light. We don't want to lose the image. We don't want to bend it. We don't want to change it. And that's important because what we're trying to do then is have really good resolution. And if we start to lose that due to refraction, if we start to lose the image, if it's going off to the side because of our different refractive indices, then we're going to be losing some of that resolution. And so our different types of microscopes are trying to utilize all these different terms that we just talked about, the wavelengths or the waves interfering with each other, so interference, taking into consideration refraction indices and what that light is going through, the image is going through, taking into consideration the different focal points, so the ability to move the focal point to be able to get it onto what is being looked at, so whether that's the eyeball or a screen of some sort. But then also we need to take into consideration magnification and then resolution, and then those different aspects of resolution, which is the wavelength that's coming in, and then how much light it's gathering. So all of these things need to be taken into consideration when we're talking about these different microscopes. So as we're moving forward in the chapter and we're talking about all the different microscopes, keep in mind these different terms, because what's being adjusted in these different microscopes are these different things. So we can adjust the contrast, and that's going to make things look different. We can adjust the resolution, that'll make things different. And we're adjusting the resolution based on the wavelength, for example, like the electron microscope compared to our bright field microscope. And then also we take into consideration the refraction indices. So sometimes we're looking through air and glass, or multiple air and glass areas, and then sometimes we add oil, for example, or sometimes we're in a machine so that we can decrease that and we have a vacuum, for example. So all of these things are going to be manipulated so that we can get various types of images and the best images that we can at the different levels of magnification. So that kind of summarizes the 2.1 for this portion, and then we're going to move into taking a look at the different types of microscopes coming up.